Hello everybody, and welcome back to another geometry lesson. Today, we're starting Unit 6. Now, Unit 6 is going to be very short for us as we get closer and closer to finals time. There are just a couple of things that we really want you to know before going into them. Unit 6 is going to be all about bisecting, so cutting things in half, something we've talked about before. It's also going to be about triangles again, but more the qualities of triangles as opposed to congruencies. So let's take a look. I briefly want to review something. We call something a segment bisector if it passes through a line segment's midpoint. So a segment bisector can be anything that cuts a segment in half as long as it passes through the midpoint. Let's say I've got a midpoint here, points A and B, and I've got a line. That would be the segment bisector. Another thing that we talked about in the past is we say two lines are perpendicular to each other if they intersect to form, specifically, right angles. So as long as two lines cross in a way that creates a right angle, those two lines are perpendicular. Keeping these two ideas in mind, segment bisector and the word perpendicular, take a guess as to what a perpendicular bisector is. Well, it's got the word perpendicular in it, so we know there's going to be a right angle. And it's got the word bisector, so we know something is going to be cut in half. I think I have a pretty good idea. A perpendicular bisector should have the properties of both perpendicular lines and segment bisectors. What does that mean? Well, it means that, for one, if we have a line segment here, it should cut this line segment in half, meaning it goes through the midpoint. So these two sides will be congruent. And I think it should cut it in such a way that it makes a right angle. This is what a perpendicular bisector is. It is something that both cuts a segment in half and makes perpendicular lines. As a more formal definition, it's actually going to look more like this. A perpendicular bisector is a line that is perpendicular to a segment at its midpoint. Bam. So let's talk about some definitions that are going to help us here in the future. The first definition I want to talk about is equidistant. And this is a word that we use just in regular everyday English. Let's say we've got a house over on this left side. And let's say we've got a tree over on this right side. As you can tell, I am the best artist of all time. And let's say that I am standing directly in the middle of them. If I am the same distance from the house, we'll call it 10 feet, as I am from the tree, I am equidistant from both. So how is this different from midpoint? Well, it never said that I had to be directly in between them. Maybe I'm standing up here, or down here, or maybe I'm standing all the way at the bottom of the page, sort of near here. As long as I can measure the distance and both distances are the same, that is what it means to be equidistant. So a point is equidistant from two figures. It means it could be anything from points to lines to line segments. A point is equidistant from two figures when it is the same distance from both. There we go. That's what equidistant means. Now, we've already talked about the perpendicular bisector. Let's turn it into a theorem because there are some really interesting properties about perpendicular bisectors. Specifically, if a point lies on a perpendicular bisector, and I'm going to pause the definition right here because I want to draw out what we're talking about. So let's say I've got, I don't know, let's say I've got a line segment that goes vertically like this. Here's point A, here's point B, and here's the midpoint. If I've got a perpendicular bisector, let's call it this line here, and a new point that is on that perpendicular bisector, well, here's the interesting thing. Then it is equidistant from the endpoints of the segment. Then it is equidistant from the segment's endpoints. So we know that the midpoint is going to be the same distance from A and B because it's a perpendicular bisector. But it turns out that P is also the same distance from A and B. If I draw out these lines, like so, and like so, they look like they're about the same length. This is true of anything that is on a perpendicular bisector. No matter where that point is. Maybe I have a point called Q. Q is the same distance from A as it is from B. Maybe I have another point, S. S is the same distance from A as it is from B. The reason why this works is because the bisector, this line that I'm going to put my pen over, is directly in the middle of A and B. So any point that's on this bisector is also directly in the middle of A and B. So it's equidistant. Pretty cool, right? Before we go on to more theorems, I want to actually practice this. So flip your page and turn to exercise 1. I want to take a look at 1A. We're asked to find the indicated measure, explain our process. So the first thing I want us to identify is, what do we have going on here? We've got a line segment, because it stops, that goes from R to P. Do we have a perpendicular bisector? Yeah. Turns out this line here is a perpendicular bisector. How do we know? Well, it's perpendicular, it's got those markings, and it's a bisector because on either side of it there's a congruency tick mark. So, SQ is a perpendicular bisector. According to our theorem, if there's any point that lies on this yellow line, if there's any point that's on the perpendicular bisector, it is equidistant from the line segment's endpoints. We do have a point on this perpendicular bisector. It's point S. We are told that it's the same distance from P as it is from R. So if this distance is 6.8, guess what? This distance is also 6.8. We can say that RS equals 6.8 due to the perpendicular bisector theorem. That's what it means to use the perpendicular bisector theorem. Here's what I want you to try. I want to see if you can try out part B here and try part E as well, using that perpendicular bisector theorem. Pause the video and give these two problems a shot. Hopefully we had a chance to try these out. Let's take a look. First off, do we have a perpendicular bisector in B? Absolutely. This line here is a perpendicular bisector because it's perpendicular to and cuts in half line segment AC. Because of that, if this length is 27, then this length is 27. CD, which is what we're trying to find, is 27. It's always going to match on both sides. If we take a look at AD, this one's going to be a little bit trickier. We've got a bunch of X's. But it's the same triangle, just with different... No, actually it has... No, it does have slightly different letterings. So we know we've got a perpendicular bisector, which means that the length of CD has to equal the length of AD. If CD equals AD, that means that 3x plus 14 should equal 5x. And we can just solve this using algebra. We can subtract 3x for both sides, giving us 14 equals 2x. And we divide by 2 on both sides. We find that x equals 7. But we're not looking for x here, we're looking for the length of AD. So let's take this length here and plug it in for this. 5 times x, or 5 times 7, equals 35. So 35 is the length of AD. Nice. It turns out that even though this theory works, the converse also works. So we have to remember back to Unit 2 when we talked about converses. A converse is what happens when you flip the hypothesis and the conclusion. In other words, the part that comes after the then comes first. So if we rewrite this, it would say, if a point is equidistant from a segment's endpoints, then it lies on the perpendicular bisector. Very nice. So what we can basically say is, if we already know that a point is the same distance from a segment, we can sort of do the opposite. Let's say we have line segment DE here, and all the way over here, we have point G, because why not? If I tell you right off the bat that DG and EG are congruent, it means that G has to lie on this green perpendicular bisector. It means that DE is cut in half, so these two halves will have to be congruent. It's sort of the opposite of this past theorem. We use it like this. If we take a look at problem C, we're expected to find the length of EG. Well, what do we know? What are we given? We know that this length here from E to H is 24, and this length from G to H is 24. So what does that tell us about point H? It means H must lie on the perpendicular bisector. This isn't just any line, this is the perpendicular bisector. So that means these two sides are congruent. If FG is 9.5, and the two sides are supposed to be the same, that means that this side should also be 9.5. We basically filled in all the lengths of this triangle. Which means, if e to f is 9.5, and f to g is 9.5, we can just use segment addition to add these two together and get the entire length, EG. EG is 9.5 plus 9.5, or 19. Let's move on. There are two more theorems in this section that are going to be used. The angle bisector theorem and the converse of the angle bisector theorem. Like I said, we're cutting a lot of stuff in half today. Before we do this theorem, I want to remind you of what an angle bisector is. An angle bisector is when you have an angle, let's call this x, y, z. The angle bisector would be the line that cuts the angle into two equal or congruent angles. So it would make this one and this one congruent. If this angle was, let's say, 30 degrees, this angle is 30 degrees. The angle bisector theorem works on that same principle. Let's say we know that there is an angle. Of course, my space to draw this angle is a little bit slim, so I'm going to make the best with what I have. Let's call this angle A, B, C. Let's also say that this angle is being cut in half. I think that is about half. We'll call this one point D. To show that this angle is being bisected, I'm going to draw these two congruent arcs. If you know that an angle is being bisected, and you've got a point on it, it means that you are the same distance away from both sides of the angle. Now, when we find the distance between a point and an angle, or a point and a line, we always take the perpendicular distance. So it's saying that these two lengths are going to be the same. Let's write this out, and then we'll do some practice to understand it a bit better. We're also going to do the converse, just because they're very related. So the angle bisector theorem says, if a point lies on the bisector of an angle, then it is equidistant from the angle's sides. That point is right in the middle of the angle. The converse of it works like this. If a point is equidistant from the sides of an angle, then it lies on the angle's bisector. In other words, if I start you with a diagram that looks like this, let's make this a crazy diagram. Let's say we've got point P all the way over here. If I tell you that this purple length and this purple length, which are both right angles, are the same, well, guess what? You can make a bisector right through that point. That is cutting the angle in half. What this presents itself as is this. We can look at a diagram. Actually, let's start with B. We can look at a diagram and try and see, is this angle being bisected? In this case, yeah. These angle markings tell us that this angle is being cut in half. If it's being cut in half, SP and SR are the same length. If SP equals SR, or RS, if you really want to call it that, that means that 5x equals 6x minus 5. Of course, we want to get x by itself, so we can subtract 6x from both sides. Negative x equals negative 5, or x equals 5. To find the length of RS, then, we can just plug in 5 for x up here. 6 times 5 minus 5, well, that's 25. The length of RS is 25 due to the angle bisector theorem. Of course, the converse is also true. If we take a look at this angle, we don't know that the angle is being bisected. There's no markings to show it. What we do know is that J to G is 7, J to H is 7. Since those two lengths are the same, it means that JF is actually an angle bisector. It's cutting it in half. If it's cut in half, then this angle and this angle have to be the same. So this one's 42. This one's also 42. GFJ is 42 degrees. I do want you to give C a shot, because C is a little bit tough. We don't have a diagram, so you might have to make one. Pause the video and see if you can figure it out. With this one, anytime you have an example that doesn't have a diagram, but you think you need one, feel free to draw it. I'm going to make this a wide angle for no reason. It could be a narrow angle, it could be a right angle, whatever. I'm going to make this really obtuse, though. If I've got an angle called ABC, that means there's a point here at a point here at A, B, and C. B's got to be the middle, because it's the middle of this. We need to make a point that is perpendicular to both A and C. So it's probably going to be right around there. BD is the length or the name of this ray. And we know that these two are the same. If DC equals 5.4, then DA should also be 5.4. Very nice. Last but most certainly not least, we have example 3. Example 3 is going to be a case where a graph is helpful even if you don't technically need it. I'm going to use the graph today just because it's going to help us visualize what's being asked, but it's not necessary to solve this type of problem. Here we go. We're trying to write an equation of the perpendicular bisector of the segment with these endpoints. That's a lot of words, so let's break it down. We know that perpendicular bisectors are always going to be just straight lines, like this, right? So if we wanted to write the equation of the perpendicular bisector, we know that it's going to be in y equals mx plus b form, because that's the equation of a straight line, slope-intercept form. For slope-intercept form, we need to find the slope, and we need to solve for the y-intercept. Well, let's get back to that in a second. We have these endpoints. P is at -2, 3, so I'm going to graph that. There's where point P is. And Q is all the way over here at 4, 1. That's Q. So we've got a line segment that's going to go sort of through here. The fact that we are asking for the equation of the perpendicular bisector means that we will have to cut this line segment exactly in half, and we're going to have to figure out what's perpendicular to it. So we can do this in any order. I'm going to start by figuring out how a line can be perpendicular to it. Well, what do we know about perpendicular lines? We know that their slopes are opposite reciprocals. So, if we can find the slope of PQ, make it negative, and flip it, we will have the slope of our perpendicular bisector. Let's do it. The slope of PQ can be found either by counting it out, because we have a graph, or if you don't have a graph, you can always just use the slope formula. y2 minus y1 over x2 minus x1. Well, if we plugged in some y values and x values, let's say that y2 is 3. That's going to be 3 minus 1. Those are our two y values. Got to go back to here for x2. x2 is negative 2 minus 4. That's going to give us 2 over negative 6. If this simplifies, we get negative 1 over 3. Okay, so the slope of the line that's perpendicular to it will have to be the opposite reciprocal. The opposite of negative is a positive. The reciprocal of 1/3 is 3 over 1, or just 3. We have the first thing we need, the slope. The problem is we don't know where the slope is going. Is it going over on this side? Is it going over on this side? Well, it's got to be in the middle. So let's take a look at what it means to be a bisector, and let's see if we can find that bisector. Since the bisector has to cross through the halfway point of these two, we can use a formula that we haven't used in a long time, the midpoint formula. The midpoint of any 2 points can be found by finding the average of their x values and the average of their y values. To find the average, you just add them up and divide by 2. So we're going to take both of our x values of these points, add them and divide by 2. We're going to take both of the y values of these points, add them up and divide by 2, and we will get the midpoint. So our midpoint, I'm going to call M. The two x values are negative 2 and 4. So negative 2 plus 4 divided by 2. The y values are 3 and 1. So we do 3 plus 1 divided by 2. Well, negative 2 plus 4 is 2. Divided by 2 gives us 1. 3 plus 1 is 4. Divided by 2 gives us 2. So our midpoint is at 1, 2, and if we take a look on our graph, yeah, I would definitely agree. That looks exactly halfway between these two. Bam, bam. So since we know where the midpoint is now, and we know the slope is 3, we can also draw the slope. We can go down 3 left 1 or up 3 right 1 to make the slope. Either way, the slope of our perpendicular bisector is going to make it go something like this. That is our perpendicular bisector. All we need now is the equation for it. So, to write the equation of this perpendicular bisector, we know it's going to be y equals mx plus b. But we know some information now. We know, for instance, that m is going to be 3, so we can fill that in right away. And we were also given a point that's on that line. 1 for the x and 2 for the y. So this is really 2 equals 3 times 1 plus b, or 2 equals 3 plus b. To solve for b, which is the last thing we need, it's the y-intercept, we can subtract 3 from both sides and get negative 1 equals b. With that in mind, we can write our final equation. Our m is 3, our b is negative 1. So in slope-intercept form, our equation is y equals 3x minus 1. And we are done. So, thank you so much, everybody. If you have further questions about these notes, let me know. Until next time, have a great rest of your day.